So imagine building a network so powerful that it tracks 10 million separate devices just in your immediate neighborhood.
Right, like just right outside your front door.
Yeah, exactly. And it can process all the data required to beam a real-time 3D hologram directly onto your kitchen table.
Flawlessly.
Right. And it can transmit the actual physical sensation of touch across oceans with zero perceptible delay.
Which is mind-blowing.
It really is. And yet doing all of this will somehow use like 90% less energy than the 4G or 5G networks that you're using to listen to us right now.
Yeah, it sounds like science fiction, I mean, honestly.
Totally. So today we are taking a deep dive into this massive, just reality-bending leap from 5G to 6G.
It really is a complete paradigm shift because, when 5G rolled out, the fundamental architecture of the internet well, it remained the same.
We just got faster speeds, basically.
Exactly. We just widened the pipes, right, to push data faster.
Yeah.
But 6G requires completely redesigning how networks operate from the ground up.
Because we're moving away from just looking at a screen.
Right. We are moving from a model of interacting with a network to literally existing inside of it.
I love that framing. Moving to 6G is essentially like going from a postal service that delivers packages to an omnipresent central nervous system that just feels everything instantaneously.
That's a great way to put it.
And to understand how that transition actually happens, we are synthesizing a few really foundational engineering documents for you today.
Some heavy-hitting research.
Oh, yeah. We're pulling from Eurocom's research on the 6G intense architecture, a massive preprint study analyzing 6G key performance indicators, and the framework review from the NGMN Alliance.
Right, the Next Generation Mobile Networks Alliance. I mean, these are the literal blueprints being used right now by telecom architects worldwide.
The people actually building the physical and software layers of the coming decade.
Exactly.
So before we dive into the incredibly complex AI architecture required to run this massive nervous system, we really need to understand the sheer scale of the demands being placed on it.
Because the applications outlined in this research force a total rethink of basic physics.
They're calling it immersive communications.
Yeah.
And the numbers are ridiculous. We're looking at target peak data rates of 1 terabit per second.
Which is, just for context, about 50 times faster than the absolute peak theoretical speed of 5G.
50 times.
Yeah. But raw speed isn't actually the defining metric of 6G. The really critical number here is the latency target.
Right, the delay.
Exactly. They are targeting an end-to-end delay of less than 0.1 milliseconds.
Wow.
Yeah. That is a tenth of 5G's latency, and we need that because we are moving away from the era of enhanced mobile broadband.
Which is basically, just streaming 4K video to a flat screen.
Exactly. We're moving out of that and into what they call holographic type communication, or HTC.
And HTC relies on opening up these sub-THz frequency bands, right?
Yeah, it does.
And these are like massive chunks of the wireless spectrum that have historically just gone unused.
Because those high-frequency waves are incredibly fragile. I mean, they don't penetrate walls well at all, and they degrade over super short distances.
But if you can build a dense enough network to actually capture them, you can transmit 3D holograms with actual depth and parallax.
Right. And with parallax, as you move your head around the hologram, your perspective changes naturally.
Exactly as if a physical object were sitting right in front of you.
Yeah. And to maintain that illusion, the network has to support 6 degrees of freedom. So it's tracking your exact physical movement in space and adjusting that remote rendering in real time.
And just that visual data alone requires a constant, uninterrupted bandwidth of, somewhere between 70 to 300 megabits per second?
Yeah, just for the visual side. But visual data is really only half the equation for immersive communications.
Right, because there's also haptic communications, which is transmitting the actual physical sensation of touch.
And there's a fascinating paradox here in the research regarding bandwidth versus latency.
Oh, right, yeah. Because sending a 3D hologram takes a massive amount of data, like up to 300 megabits.
Right.
But transmitting the sensation of touch, like a robotic arm gripping a scalpel or a virtual handshake, that only requires a bandwidth of about 2 to 5 megabits per second.
It's tiny in comparison, but the latency requirement is brutal.
Why is that?
Well, haptics require an ultra-low latency of 0.5 to 3 milliseconds, and that really comes down to human biology.
Oh, interesting.
Yeah, your visual cortex can be relatively easily tricked into seeing smooth motion at just 30 or 60 frames per second. But your somatosensory system, your sense of touch, is incredibly sensitive to time discrepancies.
Ah, so if things don't line up perfectly.
Exactly. If a surgeon in New York uses a robotic arm to operate on a patient in London, the physical resistance of that tissue has to be felt instantaneously.
Right, there's no room for lag.
None.
Hmm.
If there is even a 10-millisecond delay between the surgeon's finger moving and feeling the pressure feedback, the human brain immediately recognizes the discrepancy.
And the illusion completely breaks.
Or worse, you make a microscopic surgical error because the tactile feedback arrived just a fraction of a second too late.
Okay, I mean, I understand the biological need for zero point 0.1 millisecond latency, but let me play skeptic here for a second.
Go for it.
I look at the physical realities of our current infrastructure. Like, wait, my 5G still drops calls when I drive under a bridge. How can we possibly expect flawless, lag-free holograms?
It's a very fair question.
Because right now, data has to travel through fiber optic cables, route through switching centers, bounce off cell towers, and the speed of light inside a glass fiber optic cable is only about 200,000 kilometers per second.
Right, so there's a hard physical limit.
Exactly. If you are doing remote surgery between New York and London, the physical distance alone makes 0.1 millisecond latency mathematically impossible, let alone the processing time at all the routers.
And you are hitting on the exact physical limitation that forces 6G to change how it measures success. We actually have to stop measuring network quality purely by speed or basic latency.
Okay, so what do we measure it by?
The new metric is called presence fidelity.
Presence fidelity. What exactly is that?
It's the metric of making a virtual interaction completely indistinguishable from a physical one.
Okay.
And to achieve presence fidelity over long distances, where the speed of light is a literal bottleneck, the network cannot just be a dumb pipe waiting for data to travel back and forth.
So it has to be smarter.
Very. It has to utilize localized edge computing. The network actually predicts and renders the localized physical environment directly at the endpoint.
Oh, I see. So it's not sending the entire room across the ocean.
Exactly. It
Ah.
only sends the absolute minimum mathematical vectors of movement, and then the local network nodes dynamically recreate the synchronized visual and haptic feedback right there.
Wow. So to achieve presence fidelity, the network needs an unprecedented level of local awareness.
Unprecedented.
For a hologram to sit naturally on your real-world kitchen table, or for a local edge server to render a remote environment, the network has to actually know the exact physical state and location of everything around you in real time.
Which is where the sheer scale of the 6G physical-digital merge really comes in.
Yeah, let's talk about the density, because this blew my mind.
The organizations developing these standards are targeting a connection density of 10 million devices per square kilometer.
10 million devices
Yeah.
per square kilometer.
Yeah.
That is an incomprehensible number. I mean, that is obviously not just smartphones, smartwatches, and laptops.
Oh, definitely not. The vast majority of those connections will be what the industry calls ambient IoT, the ambient Internet of Things.
So we're moving past the era of battery-powered sensors that you have to, like, recharge or replace.
Completely. The engineering framework details these millimeter-scale sensors, categorized as classes A through C,
Millimeter scale, that's tiny.
and the most advanced of these Class A devices operate completely without a battery.
Okay, wait. How does a computing device operate, take readings, and transmit data without an internal power source?
Through ambient radio frequency harvesting.
RF harvesting. Okay, how does that work?
Think of how a solar panel works. It sits there, catches ambient light waves, and converts them into an electrical current.
Right.
Well, these millimeter-scale antennas do the exact same thing, but instead of light, they act like a net, catching the background electromagnetic radiation.
The stuff that's already bouncing around us.
Exactly. From Wi-Fi routers, television broadcasts, cellular towers. They convert that ambient electromagnetic flutter into just enough microscopic electrical current to wake up.
That is wild.
Yeah, it powers up just enough to take a temperature reading or register a vibration and then beam that tiny packet of data back to the network.
It's basically like smart dust.
That's a perfect analogy.
If you have these invisible millimeter scale particles coating a shipping warehouse or an autonomous factory or an entire city intersection, they are constantly whispering environmental data back to the network without ever needing a battery replacement.
But, if you have invisible smart dust covering a whole city, the immediate challenge is knowing exactly where every single speck is located.
Oh, right, because otherwise it's just noise.
Exactly. And that requires a massive leap in spatial positioning. In 4G and 5G, we rely heavily on GPS or basic cell tower triangulation.
Which gives us an accuracy of a few meters, usually.
Right, which is perfectly fine for driving directions.
Right.
But for 6G, the positioning moves to sub-centimeter accuracy.
Okay, getting a location fixed down to less than a centimeter using invisible radio waves seems physically impossible.
Yeah.
Especially in a city where a signal can bounce off a building or a passing truck and distort the timing.
It is impossible if you use legacy methods. That's why the 6G framework moves to carrier phase-based positioning.
How is that different?
Well, think of a radio wave like a physical tape measure stretching between a cell tower and your device.
Okay.
Legacy GPS essentially looks at the large 1-meter markings on that tape measure to guess the distance based on how long the signal took to arrive.
Right.
But phase-based positioning actually analyzes the continuous sine wave of the signal itself. It looks at the millimeter-level tick marks on the wave's phase cycle.
Oh, wow. So it's way more granular.
Much more. And by combining that microscopic weight analysis with side-link innovations, the accuracy becomes absolute.
Wait, sidelink meaning the devices are communicating directly with one another rather than routing everything up to a central cell tower first.
Precisely. It creates a dense, localized mesh.
So my phone and an autonomous delivery drone overhead and the smart dust on a street lamp.
They all continuously cross-reference their phase-based distances with one another.
That's incredible.
Yeah, this distributed triangulation allows for positioning accuracy of less than 1 centimeter for things like precision robotics, and less than 10 centimeters for tracking inventory in a massive smart factory or managing autonomous drone traffic.
So if you combine a density of 10 million constantly communicating devices per square kilometer with sub-centimeter location accuracy, the network is essentially rendering a perfect, real-time digital twin of the physical world.
Exactly. The network maintains a continuous, millimeter-accurate digital replica of physical reality.
And that is how your local edge server knows exactly where the table is for the hologram.
Right. And it's how an autonomous vehicle knows a pedestrian is stepping off a curb, even if it is pitch black outside.
It's essentially omniscient in its physical space.
But generating a real-time digital twin introduces a catastrophic management problem.
I can imagine.
If the air is filled with 10 million devices per square kilometer, human engineers simply cannot physically route that traffic.
Right, there's just too much of it.
You cannot sit in a control center and manually write software rules for every possible environmental variable or bandwidth request.
It would be impossible. So what's the solution?
The network has to grow a brain to govern itself.
Which is exactly what the Eurocom researchers are attempting to solve with their 6G Intense architecture.
Right.
The core innovation of 6G Intense is native AI. In the 5G era, artificial intelligence was largely like an application running on top of the network. You sent data to a central cloud server, and AI processed it and sent an answer back.
But in this new architecture, AI is embedded directly into the physical and MC layers of the network itself.
So the actual silicon inside the local antennas and edge routers is inherently running AI models.
Yes. And that native AI enables a profound shift in network management called intent-based networking, or IBN.
Intent-based networking. Okay.
Instead of a human network engineer typing in complex command line codes to configure routers or allocate frequency blocks, humans provide abstract operational goals. Intents.
You tell the network what you want, not how to do it.
Exactly.
So a hospital administrator might issue an intent that says, ensure 0 latency and 99.999% reliability for all robotic surgery bays on this campus.
And then the network takes over.
Right. The network's native AI autonomously calculates the billions of micro-configurations required across the edge servers, the radio frequencies, and the ambient IoT sensors to make that happen.
And the interface for providing these intents relies heavily on agentic large language models.
LLMs, like chatting with an AI.
Yes. Users will negotiate with the 6G network using natural language.
This is wild. So if a factory manager asks the network for a massive dedicated slice of bandwidth for a new fleet of inspection drones, but the network knows it's currently dedicating spectrum to a nearby emergency response,
the agentic LLM will literally converse with the manager in plain English.
So the network functions as an autonomous digital butler. It will literally push back on human requests, saying I cannot fulfill this bandwidth intent right now due to emergency priority, but I can offer you a slightly lower frame rate for your drone cameras, or delay the data sync until 2 a.m. Do you accept?
Yeah, that autonomous negotiation is absolutely vital. But the true test of native AI is what happens when intents genuinely conflict and there's literally no time to negotiate.
Right, what then?
The 6G intense architecture uses hierarchical reinforcement learning, or HRL, paired with reinforcement learning from human feedback to resolve those conflicts instantaneously.
Walk through how that HRL conflict resolution actually works in practice. Because in the real world, a hospital needs life or death latency. A smart factory needs to run 1,000 precision robots. And I don't know, teenagers down the street are playing a fully immersive haptic VR game. Priorities clash constantly.
They do. So the HRL system acts as a multi-tiered judicial system for data.
A judicial system, okay.
It's been trained by human engineers on fundamental priority matrices. So when the teenager's VR game requests an ultra-low latency pathway and the hospital requests it at the exact same millisecond, the conflict hits the top layer of the HRL algorithm.
And it makes a decision.
Instantly. The system evaluates the environmental context, calculates the mathematical limits of the local spectrum, and autonomously cascades new operational policies down to the physical routers.
Without a human engineer ever intervening.
Right. The edge nodes instantly throttle the VR game's frame rate and lock in the dedicated pathway for the surgery. Autonomous mathematical conflict resolution at the microsecond level is really the only way to scale network of this density.
But, to allow an AI to autonomously rewrite routing policies and throttle bandwidth at the hardware level, the physical infrastructure of telecommunications and the massive monopolies running it must fundamentally reorganize.
Oh, absolutely.
Because a brilliant AI brain is useless if the underlying hardware is fragmented across a dozen different corporate vendors.
And that physical reorganization is the blueprint phase of the documents. The Eurocom architecture outlines a foundation called the NCF, the Network Compute Fabric.
The NCF.
The NCF's entire job is abstraction. It takes all the physically disjointed resource pools, the 6G radio towers, the massive centralized cloud data centers, the deep edge servers on local street corners, and it abstracts them.
So they look like one single unified computer to the native AI.
Exactly. The AI doesn't see a Nokia tower here and an Amazon Web Services cloud server there. It just sees available computing cycles and spectrum.
And sitting above that abstraction layer is the DMO, the domain manager and orchestrator,
Right.
which is basically the cognitive brain translating those natural language intents into actual service deployments across the unified NCF.
But this introduces a massive shift in telecom business models because the architecture also introduces the TMP, the Tenant Management Platform.
Okay, what does the TMP do?
It fundamentally changes who provides your network service. Historically, the massive telecom corporation that spent billions laying fiber optic cables and building cell towers was the sole entity that could sell you service.
Right. They own the pipes, they sold water.
Exactly. The tenant management platform turns that physical infrastructure into a blank canvas, allowing external entities to act as virtual operators.
See, I look at this from a business perspective, and I have to wonder why the infrastructure owners would ever agree to this. If I own the towers, I don't want to become a dumb, invisible pipe while someone else takes the profit.
It's a tough pill to swallow for them.
But under this PMP model, a software company that specializes entirely in smart factory automation can lease a highly specific AI-managed slice of the network directly from the tower owner.
Right.
They don't own a single physical cable, but they sell that optimized vertical service directly to a car manufacturer. It democratizes the innovation layer, even if it forces the tower owners into a wholesale model.
Yeah, and the transition to this open AI-driven model is heavily regulated. The framework established by the NGMN Alliance and the ITUR mandates strict backward compatibility.
So they can't just flip a switch and break the old stuff.
Exactly. As this global transition occurs, 6G deployment absolutely cannot compromise existing legacy services.
Right.
You cannot destabilize a city's 5G public safety network
Yeah.
or 4G LTE communications just to carve out spectrum for sub-THz holograms.
Which makes sense.
Eh.
But that brings us back to the most counterintuitive aspect of this entire engineering feat. We are detailing the construction of an omnipresent nervous system that tracks 10 million devices per square kilometer, powers real-time digital twins of cities, and runs pervasive artificial intelligence at the silicon level.
It sounds power-hungry.
Logically, the power consumption should be catastrophic, yet this is designed as a massive carbon reduction project.
It is. Energy efficiency is a hard-coded prerequisite in the standards. The industry is targeting extreme metrics, specifically aiming to transmit 1,000 terabits of data per joule of energy.
A joule is an incredibly small unit of energy. Like, it is roughly the amount of energy required to lift a small apple 1 meter off the ground.
Right. And with that one apple's worth of energy, the 6G architecture must move 1,000 terabits of information.
That is insane.
The ultimate mandate is a 90% reduction in overall network energy consumption compared to the legacy LTE networks of the 4G era.
But how does the AI actually achieve a 90% reduction while handling exponentially more data?
Through incredibly aggressive microsecond-level resource management. Because the native AI has a real-time digital twin of the environment, it knows exactly where the demand is.
Ah, I see.
It uses those batteryless ambient IoT sensors to track human and device movement. If a sector of a smart factory is empty for even a fraction of a second, the AI instantly microsleeps the antennas serving that area.
So it's constantly flicking switches on and off.
Constantly. It dynamically shapes radio beams only to the specific coordinates of active devices, rather than broadcasting a wide, energy-heavy signal in all directions. It ensures not a single watt of power is wasted on empty space.
The sheer ambition of that engineering is staggering. We are moving from a world where we stare at rectangles of glass to access information into an era of immersive communications where presence fidelity replaces raw speed.
We covered the physical-digital merge, where ambient RF harvesting sensors and phase-based positioning allow the network to map physical reality down to the sub-centimeter.
Right. And we unpacked how the 6G intense architecture embeds native AI into the hardware itself, using hierarchical reinforcement learning to autonomously negotiate resources and cascade policies in real time, all while targeting a 90% reduction in energy usage.
The smartphone in your pocket is about to transition from a screen you look at into just one tiny node in a global autonomous nervous system.
The environment itself becomes the interface.
It really does.
But operating a perfect digital twin of reality introduces terrifying security implications. If the network accurately tracks every physical object and human in a city, a data breach would be catastrophic.
Yeah, privacy takes on a whole new meaning.
The frameworks we analyze note that to secure this omnipresent network, 6G will actually integrate quantum communications.
Specifically, quantum key distribution, utilizing qubits rather than traditional binary encryption keys.
And this is fascinating because traditional encryption relies on incredibly complex mathematical passwords, but quantum encryption relies on the literal laws of physics.
Right, because a qubit exists in a fragile state of superposition.
Exactly. And the fundamental laws of quantum mechanics dictate that the moment a qubit is observed or measured, it changes its physical state. It collapses.
And the security implications of that collapse are profound.
If a hostile actor or a hacker attempts to intercept or spy on your quantum encrypted data stream, the mere act of them looking at the qubits physically alters the data's existence.
It's self-protecting.
Yes. The observation destroys the key instantly, rendering the data useless to the hacker and immediately alerting the AI to the exact location of the intrusion. So, our future digital privacy won't be protected by software firewalls. It will be protected by the fact that data literally alters its own physical reality if someone tries to peek.
Which is a brilliant solution to an incredibly complex problem.
Something for you to ponder next time you pick up your phone.
A fascinating architectural reality to look forward to.
Indeed. Until our next deep dive, keep looking beyond the screen.